Welcome, everyone. My name is Brendan Hassett. I'm a professor of mathematics here at Brown University. I'm also the director of ICERM. ICERM is the Institute for Computational and Experimental Research in Mathematics. Our core funding comes from the National Science Foundation. We also get support from the Simons Foundation as well as individual and academic sponsors. Welcome. I just wanted to say a little bit about what we do. Our programs are at the interface between mathematics and computation, mathematical sciences, statistics, everything covered by DMS. Our core support comes from the National Science Foundation. Yes, and we have programs where breakthroughs in the mathematical and statistical sciences lead to new algorithms and new computations, but we also are interested in experiments, computational experiments that will inform research progress. And so that feedback loop is something that we intend to and hope to encourage in our program. And so this is actually part of a longer series of events that starts now. The Blackwell Tapia Conference will run tomorrow and Saturday. And so this is sort of a kickoff event. So for those of you that are coming from Blackwell Tapia, welcome. It's great to see you. So I want to talk a little bit about the lecture series. Let me introduce Professor Kimberly Sellers. So she is the chair of the statistics department at North Carolina State University, which is one of the top statistics department in the country, if not the world, really one of the powerhouses in the field. And so she leads this nationally important institution. Her work is on counting. And I don't know if the count is sort of a double meaning.
It is.
And so I am a number theorist, and the only numbers I do is like 0, 1, 2, 3, 4. And normally I can't do any statistics because, like, how do you pick a random integer? Who knows? Well, there's a lot of research in terms of how to do a statistical analysis of counts and come up. And I won't say anything more about it because I don't know very much about it, but this is certainly part of the focus of both Professor Sellers' work and also perhaps related to some of the things that will be in the book that we'll hear about. So Professor Sellers did her undergraduate and master's degree at the University of Maryland, College Park. She did a doctoral degree at George Washington University. She's done many things, many national leadership roles. She is an elected member of the International Statistical Institute, a fellow of the American Statistical Association, and also a fellow of the Association for Women in Mathematics. So I've talked too long already, so let me hand the microphone to Professor Sellers.
Thank you so much for the warm introduction. And it's worth saying, you'll be happy to know that the premise behind this model stems on a focus on small count data. So this works in your realm. Let me more broadly thank ICERM for this invitation and also the Blackwell Tapia Organizing Committee for the conference that is extended through the weekend. It's worth saying this is a full circle moment for me because I was here as a student. Wait, no, not a student. What was that? Well, let's say I was here before, and I was having a surreal experience coming in here into this lecture hall because I can remember sitting in these chairs. I'll admit, I thought it was earlier than it was. Apparently, I was here in 2012, so I was very much a faculty member at that point, but I'll admit, I thought I was even here as a student. So I guess my worlds are just blurring together at this point. Nonetheless, as was noted, yes, this is a play on words here with my title. Count on me to write a mathematics/statistics book. I debated whether to call it a stat book versus a math book because, as it was relayed in my introduction, I do come from a math background, and I am very much labeled a mathematical statistician. So I straddle the fence, as you probably heard, even in terms of my attendance at joint math versus joint stat as well. So I dipped my toe in the math world. Okay, so see, you can tell I'm used to a podium. I didn't need that. All right, so yeah, me write a book. I have to say, the thought of doing so brought on the following reaction. And honestly, it still does, even though the book is done, okay? I still struggle and grapple with the idea that I have written a book. Why is that? Well, for one, I had no plans of doing so, okay? This was not in my thought process, right? As an academic, I mean, we know the drill to be writing papers, and at least in this field, right? It's more so writing papers than writing books. And so, I was in that realm and never even thought of the idea of writing a book. And beyond that, just, like I said, staying in my lane. So how did I get from that space to this product? And that's going to be the topic for the talk today. So I'm really dating myself probably by making a reference to A Tale of Two Cities. But for those of you that are familiar with this classic novel, let me at least assure you that my story does not begin nor end the way that this book does. Let's start there. However, the book took me to a different title that does make sense: A Tale of Two Icons. What do I mean by that? I introduced to you icon number one, David Blackwell. Okay? It seemed only fitting to draw reference to Blackwell because the forthcoming conference for this weekend is Blackwelltopia. So for those of you unfamiliar with David Blackwell, he was a statistician, very well noted and respected for his work in probability theory and game theory. He was the first Black scholar to be admitted to the National Academy of Sciences. He was the first African American to be tenured at UC Berkeley. And for context, it's worth saying when he was first an academic, he could not obtain an academic job at any predominantly white institution initially. So to go from there to Berkeley, for a second I thought I had Berkeley misspelled, yes, is of course a huge feat. He's most widely known for the Rao-Blackwell theorem. And so if for those of you, I should have asked, are there statisticians in the audience? Look at that, low counts. See, I got two. This is gonna be a theme. Okay, so for the statisticians in the room, or even if you're not a statistician, the reason that you can at least appreciate this, the Rao-Blackwell theorem is a fundamental theorem in statistics. Every first year grad student learns this theorem, and it's attributed to, as you can see, actually two names, C.R. Rao and David Blackwell, who at the time when I learned of this theorem were both still alive. So it also speaks to the relative youth of the statistics as a discipline, okay? And he was posthumously awarded the National Medal of Science by President Barack Obama in 2012. But as you can see, he unfortunately had passed on by then. So you may ask yourself, how do I connect with David Blackwell? There are at least a few people that will know the why. I take you to the first conference for African American researchers in the mathematical sciences, or CARMS. For the first CARMS, I was an attendee. This is back in 1995, after my first year in grad school. There I am, seated, and David Blackwell. Ilya, I can see you trying to point yourself out. I think you're somewhere around here or somewhere. Am I right? Right? There's Ilya. So Ilya Hicks, your Blackwelltopia Prize winner, and I were both grad students at the time of the first CARMS, along with many others. And there's so many heavy hitters in this picture. I can't begin to tell you. But this was, I think at the time, a 4-day conference, if I remember correctly. Remember, this is 95, so it's been a little while, okay? But nonetheless, the point to this introduces the first lesson. What is the first lesson for you? I should say, for context, I have 10 lessons or 10 tips for you, okay? So the first one is the following. Don't be afraid to put yourself out there. To understand the context, remember what I said about CARMS. I had just completed my first year as a grad student. At that time, I was at the University of Maryland, and Dr. Raymond Johnson, for those of you that know him, Ray Johnson was one of the organizers for CARMS. Here's Dr. Johnson there. And he got several of us to this conference. And in fact, this was my first conference. So I think I should offer that for context. So here I am, like an innocent sheep, just trying to figure out my way through the world. And admittedly was very intimidated by the magnitude of what I was experiencing. And so in particular, with David Blackwell, like I said, I had just learned the theorem with this man's name in it. And to now see him in person was intimidating. It was overwhelming. And so admittedly, I just watched him from afar. But to my recollection, I don't think I ever approached him. And that was my one and only time meeting him in person or seeing him in person. And so to this day, that does serve as a regret for me. But I still claim it that we're at least in the picture together. And so moving on, as I said, tale of two icons. The second is David Cox. For those of you unfamiliar with David Cox, he wrote or co-authored more than 300 manuscripts. He's best known for the Cox proportional hazards model, Box-Cox transformations, et cetera. Since I recognize I have a diverse audience here, it's easiest to offer reference with the Cox proportional hazards model. For those, like if you watch the news and you hear some sort of report that says, I don't know, let's say, for example, maybe smoking impacts, the chances of death by this magnitude, that, at least once upon a time, was easily attributed to the Cox proportional hazards model, okay? So his work spanned lots of applications in society. He was the first recipient of the International Prize in Statistics. And if I've not convinced you enough of who he is or was as a person, let me introduce it this way. David Cox was not Mr. Cox. He was not Dr. Cox. He was not Professor Cox. This man was Sir David Cox, knighted by Queen Elizabeth II, and yes, I mean that queen, Queen Elizabeth, for his work in statistics. Notice I do this every time when I talk about him, knighted, like knighted. Knighted. The man is Sir Cox, okay? So that said, and like I said, this is for his work in statistics, okay? So it boggles the mind that you can reach that level of stature. Now that said, how does this connect with me? Lesson number 2. Don't make the same mistake twice, okay? CARMS was in 1995. In 2000, I had my first international conference, the Mathematical Methods and Reliability Conference. Here I'm pictured with my advisor, Noser Singh Purwalla, from George Washington University, and the legion of people around him were at the time present and former students, okay? Noser was one of the plenary speakers at the conference, and each of us was likewise presenting in some capacity, okay? Well, interestingly enough, David Cox was another plenary speaker at the conference. In fact, he was the first plenary. And of course, for those of you that, that have been in this lifestyle for a minute, right, that first plenary is usually a big draw, right? And obviously, so David Cox fit that description. He gave his plenary, and afterwards, I found the nerve, I found the oomph and the ability to approach him, introduce myself. Oh, Sir Cox, it's such an honor to meet you, blah, blah, blah. Can I take a picture with you? oh, sure. And we got a picture together. And what did I do with that picture? I went and showed every person that I could at this conference. Do you see what I got? I got the picture with David Cox. I even showed my advisor. I got a picture with Sir David Cox. And he goes, you've never asked me for a picture. But I see you all the time. This is Sir David Cox. And even he got a good laugh out of it. And I took this picture home. I traveled back to DC at the time. Of course, I'm at GW. And I'm sending this to all of my grad school friends now, right? On email, so that says a lot, right, as to what technology was at the time. So I'm sending this hard email, and the title reads, I think I just became a statistics groupie. But when I explained why, they responded, you got to meet Sir David Cox. And so we were all in the same boat. And so let's hold on to that for a moment, because Cox will come up later in the talk. But I'll move on to lesson 3. As an aside, I just want to say, third lesson, don't let certain detours derail you in your goals and your mission. You can still reach or even cross the finish line. What do I mean by that? I've had my share of windy roads. There's always this perception that your career, your educational experience, your career is going to be the straight path, straight and narrow. But I would argue, I think for more people than we realize, that's not necessarily the case. It's just that we don't necessarily open up about that. For me, that was true in graduate school with qualifying exams. As I transitioned into life as a faculty member, I changed my research path. And through it all, it's worth saying, life doesn't stop just because you're in grad school or have a career. Okay, so I just wanted to mention these as an aside. These are all stories in themselves that I'm happy to share, but in the interest of time, I probably have the ability to do so. But I am very transparent about my experience. All that said, let's move on let's see. So remember the conference was 2000. I graduated in 01. And so what is lesson number 4? You get to work, right? Of course, I've not really stopped working, but now it's just in a different space or a different environment. And so what did that look like? Well, for me, my work path is such where after finishing my Ph.D., as I like to tell it, I moved to the other side of the classroom. I spent 3 years at Carnegie Mellon as a visiting professor in statistics. I spent another 2 years at UPenn in biostat as an assistant professor, but in what they call a clinical educator track. So I was more of a collaborator to scientists in that space. And then from there, I completed a circle, if you will, rolling through Pennsylvania, back to DC, to Georgetown University. I was actually the first statistician hired in the then math department with the goal of creating or helping to create a master's program in applied math and statistics. But at that point, they didn't have any statisticians in the faculty. So it was actually an exciting opportunity to develop in a more elaborative statistical curriculum at both levels, undergrad and grad. And of course, in no particular order in this role, for those of us that are academics, you all know the drill, right? Research, teaching, service. So I'm writing papers. For me, being in statistics in particular, but I guess in this day and age, we're all having to write code for our works as well. Giving talks. Thank you for letting me continue the tradition. Mentoring students at various levels, seeking external funding, et cetera. And so this takes me to my next lesson. Through it all, you're building your network. Who is your network? Really, even as students, you have a network, right? those are your fellow students. Those are your colleagues at this level. But at the faculty level, of course, you have your colleagues in the department and outside of the department. You have mentors, both official and unofficial. You have collaborators with whom you've developed relationships. And like I said, advising on any level of front and with any sort of purpose. And so I do encourage you to be very generous in your pursuit of building that network, because you never know what can come of it. As an example, I introduced to you Galit Shmueli. Galit and I have a very interesting history. If you remember that 2000 conference, that Mathematical Methods and Reliability, Galit and I first met at that conference. She and I were both grad students, and we happened, I mean, this is fate. We just happened to be assigned in the same session where she spoke before me, okay? And that's how we met. We're both speaking in this, coordinated session. We didn't know each other. It wasn't organized in that way for us to keep in touch. But, you meet each other, you greet, very nice to meet you, all the best to you in your world. And we separate. Well, remember where I was where I went after my Ph.D.? Carnegie Mellon. I show up at Carnegie Mellon. There she is. She was a postdoc, a year ahead of me in her postdoc. So she had a 2-year postdoc while I had a 3-year visiting faculty position, but there we are together. Oh, small world, right? So we reconnect there. She goes on out of her postdoc, and maybe at the time went straight to Maryland. I'll admit I can't remember now, but let's say she's at Maryland. Eventually she's there. That's the whole point to this. And remember, I eventually make it to Georgetown. So here we are now in the DC area together. We connected 3 times in this span of our careers together. And so by that 3rd time, we're saying, you know what? Apparently, a higher being wants us to work together. So I think we need to figure this out. Okay, so it turns out so when we were at Carnegie Mellon, I was working on a different line of research at the time, but that is where she got into this, what you are now hearing of, this Conway-Maxwell Poisson Distribution. That's where she was exposed to it and did some work on it. And so fast forward to us connecting, she's like, yeah, I've looked at this distribution, it seems pretty interesting. Something I would love to do is move this into developing a regression model for it. Oh, that sounds cool. And when we're talking it through, I mean, it was arguably almost like a low-hanging fruit in terms of the type of work that I had learned in my math stat courses. And so it's like, oh, this is a nice, fresh way to utilize the tools that I had learned as a grad student and just carry that work forward. And carry it forward we did. We eventually had this paper in the Annals of Applied Statistics. And so now I'm going to show my, need to prove myself, forgive me, with a little bit of mathematics. I tried to avoid it as much as I could, but I felt like I wouldn't be, a true mathematician or statistician if I didn't at least show a little something. So to offer some context behind what is known as the Conway-Maxwell Poisson Distribution, and more importantly, the larger regression, is that you can think of it as a generalization of at least 2 popular regression models. The first is a logistic regression. The idea behind a logistic regression simply says that the outcome of interest is a binary outcome. So you could get a heads or a tail. You get, the outcome is to the left or to the right. You take something that only has 2 outcomes, assign one of them a value of 1, the other a value of 0. The one that is a 1 is typically the value of interest in your narrative. And so there's an underlying a Bernoulli distribution that represents this idea of, shall we say, the coin toss or two outcomes. Through a regression, it comes through this log odds relationship, this model. Here is just a simple illustration where you can see the raw data are representing these x's. And so here's a scenario where you can imagine if the amount of dosage leads to a healthy outcome versus not. You can see this sort of S curve or logistic curve representing the shape that approximates what's happening in this relationship. More broadly, Poisson regression takes the scenario where your outcomes are integer valued, count data, okay? And we do typically think of this in a small count space, as you'll soon see why. The underlying distribution for those outcomes is assumed Poisson model. Here I'm just showing you the probability mass function associated with it. And to the right, you are seeing a representation of how the data can be distributed for different values of a rate parameter, lambda. And so even from this illustration, you can see that as lambda gets large, notice that the distribution starts to look more like a bell curve. Okay, so for us as statisticians, we refer to the bell curve as a Gaussian model. And so notice what it's basically saying is if your count is large, a lot of times you can approximate with a normal distribution. There's a lot of traditional classical regression theory behind that. But when those values are small, you have to take the discrete nature into account. Okay, so that's the focus of my attention. In a regression space, now the frame of reference is what we refer to as a log linear model for obvious reasons. I always say as statisticians, we're very literal in our terminology. Okay, so this linear model relates to the log of, in relation to the rate parameter, which is serving as our mean. All right, so if you've had an intro probability class, one of the things that I am sure your instructor noted to you, I certainly have done the same thing, is that one of the draws behind this distribution is that if you know lambda, you essentially know everything about the distribution because it represents both the mean and the variance, for example, okay? And so notice that in context, we can think of this as, in relative terms, quite literally, where this goodness of fit equals 1. So this notion represents something that's referred to as equidispersion. But in real life, data don't tend to conform to this idyllic constraint. More often than not, the data are over-dispersed, meaning that there's more spread in the data than that represented by the mean. But there's also a notion of under-dispersion, where the spread is tighter than what you would see relative to the mean. And so the idea behind Poisson is that they introduce just one extra parameter and build the distribution from the ground up. It actually stems from a flexible queuing model problem where Conway and Maxwell, as you see, like I said, from the ground up, build this two-parameter generalization of Poisson. And so here I present to you the resulting probability mass function, where lambda you can still think of as that rate parameter only in the special case of Poisson. So more broadly, let's call it an intensity parameter. Meanwhile, you have this second parameter, nu, that serves as a dispersion parameter. So that's going to be a measure of the spread in the data. Nu, notice, is a non-negative value where if nu equals 1, it simplifies to your Poisson model. For nu otherwise, it takes, as I like to say, more of a reciprocal relationship. So when nu is greater than 1, it's actually capturing data under dispersion. For nu less than 1, it's capturing over dispersion, okay? And then finally, you have this z function here, that's this infinite sum. That is simply serving as the normalizing constant, if you will. Because if you think back to your axioms of probability, we need the probabilities to all be non-negative, and we need them to sum to 1, okay? So this is just achieving that goal. Now, what's interesting with this is that just with the addition of one extra parameter, I not only capture the Poisson model as a special case, but I capture two other classical distributions, the geometric and the Bernoulli distributions respectively. And so what the CMP is doing is representing, if you will, an overarching or umbrella distribution that captures 3 classical distributions as special cases, and it just spawns everything in between. So there's a lot of flexibility here. Here I'm just offering a quick illustration of, so that you can appreciate how the change in the dispersion parameter impacts the distribution. So what you'll notice is that for 5 of these 6 figures, they all have the same intensity parameter of 3. The one in the upper left, though, is under the special case where nu equals 0. So if you noticed in the chart on the previous slide, in that case you need, in fact I'll take it back, you need lambda to be less than 1 in order for my infinite sum to converge. Okay, so just for illustrative purposes, I just gave it a different value of 0.3. But what you can see is that for nu equal to 1, we have our Poisson model where the rate parameter is 3. But notice, as I said before, when nu is less than 1, it has a larger spread. For nu greater than 1, it has a tighter spread. Okay, that's basically the message that you want to see here. Now, in particular, we can see the illustration of the 3 special cases. Here we have our geometric model. So for those of you unfamiliar with statistics, the geometric model basically looks at or represents a distribution, in this case, where you're counting the number of failures until your first success. Okay, so you could start off with no failures, 1 failure, so and so, until you hit your first success. That's what a geometric does. In the case of Poisson, like I say, you can think of it as just your counting distribution. The third case, if you remember from the table, the idea is that nu is going to infinity. Interestingly enough, here in illustration, my nu is only going to 10. So it didn't take too long to at least have an idea of what's happening as nu goes out to infinity. And in fact, what are you seeing here? You're seeing a distribution with only, shall we say, two bars, right? That is precisely your Bernoulli distribution. Okay, so with that said, like I said, here are Galit and I working on this, building this regression model. And so the first thing we had to do is figure out exactly how the model should be represented. And lo and behold, after lots of work, we came up with this. Now you may ask yourself, that took a lot of work? Sure doesn't look it. Well, here's why it wasn't so obvious. While on the surface, this looks exactly like what you had for the Poisson model, if you recall, and it is. But the difference for us, that lambda that you see here is not the mean. Normally, your regression model relates a function for the mean in relation to other variables. Here, the lambda is actually a function of a more elaborate representation that we can't actually just write down, okay? But the mean is in there. So it's some function of the mean. So in the end, this is still what's referred to as a generalized linear model. It's just that it wasn't so obvious to get there. And so I sit on this for everyone to appreciate. This wasn't so obvious, okay? So yes, it took some time, but when we finally got there, there's even a greater significance to this because, like I said, it captures the special cases. In the case of Poisson, this is obvious. But it turns out to even capture that logistic regression model that we looked at before. And so again, we have a regression that spans classical regressions. So we have all of these results in terms of estimation, hypothesis testing, and the like, and we even create an R package for it, com-Poisson-reg, okay? And so as you can see, it's now in its in version 8.1. And so like I said, it can do all these things, even more than what's being presented here. And since we are rolling into Blackwell Tapia over the weekend, I thought it would be an interesting exercise to see how to utilize my package in the space of looking at the numbers of PhDs from African Americans in statistics. So as you see, these are data that I was able to obtain through the ASA, and it's looking at the number of PhDs in statistics from 2011 to 2023. It is important to note that the data do break down into subdisciplines. So these are statistics degrees. It does not include biostatistics, which is its own discipline. Okay, and so you have a sense of the data. Already from looking at it, you can probably guess how the outcome is going to go, but nonetheless, I will introduce how to utilize this Poisson-Reg package to study the data as well. It turns out that if you look at the goodness of measure, there's a slight reference to under dispersion, so it seems warranted to consider Poisson-Reg as a means to model the data appropriately. We looked at a log linear model for both lambda and nu, and when running it through the package, what you see is that the outcomes under this model turn out to not be statistically significant for both the model associated with lambda and nu respectively. With regard to nu, it's more important as the focus right now, because what you're asking is if there is significant data dispersion such that I cannot use the traditional Poisson model. Okay, that's the real underlying question right now. The fact that we have a large p-value here says I don't have to go through the trouble of this more elaborate model. I can simplify my life and just look at Poisson regression. And so what does Poisson regression give you? When you run that, you still get a result, at least in relation to time, that says that we don't see a statistically significant change over time. Okay? This all makes sense. So that said, let's understand what's happening with the data more simply. Just looking at a histogram of the data, and don't read too much into the gaps, that's just the way R presents discreteness. Let's see. When we now look at the model just more plainly, that we're not considering it over time, just asking what is happening in the data, if you will. Just trying to get a straight estimate for lambda. Notice that, and for nu. So if you look up top here, you have large, it's probably too small for you to read, so trust me when I tell you, there are still large p-values associated with the estimates for lambda and nu respectively, okay? So again, focusing the attention first on nu, if you look, I can point you further down. If you look here, notice that the estimate in the raw sense at 1.35 with a fairly large standard error, what that's saying is the confidence band around for nu covers 1, okay? And so what I'm saying is, again, you can't really throw away the idea of a Poisson model being sufficient. And so that said, let's look at that Poisson model directly and just understand a potential estimate for lambda. Remembering that this is initially presented on the log scale, we get now a statistically significant result. So that's telling you that the count is something different from, I guess, e to the 0, so different from 1. And what does that count wind up being, an estimate? Just over 5. Okay? So what does this mean? Essentially, that on average, there have been 5 African Americans to get their PhD in statistics. Now, what do you make of this? There are many stories that you can think of. I think we can all agree that 5 sounds like a relatively small number. I don't dispute that. At the same time, though, as someone who was one of the few, once upon a time, I can remember a time when the count, and I don't have the slide here, but the numbers were still small, but for all of mathematical sciences, to where you couldn't even parse out statistics, or statistical sciences, I should say. And notice now we're in a space at least where we can parse out statistics from biostatistics. So my hopeful self is that we are able to do so because the numbers are growing in some sense. I have not checked this for accuracy, but the eternal optimist in me would like to believe that. And I should say, for context, I was one of, I graduated in '01, and I believe the number is 6 Black women in mathematical sciences, all of mathematical sciences that year. And I know a few of them. Yes, like that's how it goes. Sure.
So as a number theory, something that's striking is that there's so many even numbers there and odd numbers.
So I'm going to assume no, just because I don't know that people would know each other like that to pair up like that, right? Because again, the count is so small. But of course, at the same time, I mean, when we were coming through school, that's when these sorts of conferences were just beginning. So I'll admit I don't know, but I would doubt that there's something to it. But anything's possible. Yes. Mm. For computer science, I'd actually be surprised. But in the same breath, maybe not. I think part of what's going to be interesting as we move forward in trying to collect these types of data is that the disciplines are becoming more interdisciplinary to where I think it's going to be very difficult for one to then try and categorize, right? Okay. More fruitful, yeah. So that's a great question. I'm going to assume no, but I'd have to go back and look. I mean, the data are all available and accessible through the ASA website. And I do remember it being parsed out more finely. But like I said, for me, I was motivated by looking at simply statistics because that is the area from which I came as a mathematical statistician, if you will. So I chose to focus purely on the statistics number as opposed to look more inclusively at all of statistical sciences. Was there a question? So another great question, and I guess I'll answer this from two angles. That's something certainly worth considering. Obviously, I didn't do that here. I was just doing a quick, this was really meant to be more of a look what my package can do example. That's timely, but I can say that our package does have the ability to account for offsetting as well. Yeah. This was all very last minute though, so forgive me for not being as accurate as I should have been. Okay, so yeah, look at that. We're only up to lesson 6, so I'm going to speed up the rest of this. But now to lesson 6. Oh, right. I had to remember where I was here. Yeah. So remember that was work initially with Galit, but of course the example was something far more recent, and it's just one illustration of this notion of staying on your grind. So what I mean here is, yes, Galit and I did this project together for a regression model, but even while working through that space, I could easily see other ways in which this distribution could be beneficial and just sort of in terms of broadening space of study for count data. And so as I like to tell it, I spent the next 10 years running this sucker into the ground. I looked at all sorts of different applications and areas of statistical methods. You may think, she made a mistake, she put this up. No, I didn't, because the point is we're still doing all the same stuff, right? And so I'm just doing more of the same. So what does that look like? I'm giving talks all over the place, out here just talking about CMP and other things, and writing papers, some with collaborators, some as solo authors. This one in the back actually has a funny story. So to explain, well, as the title reflects, I developed a generalizable control chart. So control chart theory is one of several areas of statistics where you're trying to understand when a state can fall out of control, okay? And so there's a Poisson or a C chart that is very standard, and I just generalized that to use Poisson. What's funny about this, as an aside, one of these many conferences that I attended, Galit happened to be there as well, and just prior to this getting published, I happened to share the work with Galit just to get her take on it. What did she think before I submitted, and so she thought it was interesting and everything. Oh, that's really cool. At this conference, there was a prominent statistician in the reliability and engineering statistics space that happens to approach Galit while I'm standing there next to her. And through the course of the conversation, this gentleman happens to change the subject to, oh, I don't know if you know. Now, he knew about Galit's work with Poisson, but he didn't know that I was in that space now. And so he says to her, oh, there's this fascinating work that just came out in QREI where someone built this generalizable control chart off of Poisson. And I'm standing right there, right there. And even I'm sitting here thinking, is he talking about my work? And sure enough, he was. And luckily, I'd shown Galit that paper. Why? Because she was able to say, yeah, that's Kim's paper. Let me introduce you to Kim. And I've had other instances where I've been at conferences where, I'm sitting there, minding my own business, or slowly trying to collaborate, or not collaborate, but interact with others. And those of us that are in the field, we know how this goes. Well, what do you do? Well, I work in count data modeling. Really? What's your name? Kimberly Sellers. I'm such a fan of your work. I still freak out over this, but it's nice to know that people are familiar with the work. It's very humbling. And I say all this to say, well, do you remember lesson 1? What was lesson 1? Don't be afraid to put yourself out there. Let's fast forward into 2014-ish, somewhere around there. Georgetown has the ability for an in-house or within university opportunity to travel abroad to the University of Oxford. And so it's a competitive experience, but you get to spend some time there. And I decided to throw my hat in the ring, okay? And so to make myself as marketable as possible, I took the preemptive strike of reaching out to various faculty at the University of Oxford in statistics. Just putting out cold calls, cold feelers, cold emails, okay? Because what's the worst that can happen? They don't respond. Okay, but what if someone does? Well, guess what? I found out someone did. Someone did respond to my reach out to potentially collaborate. Sure, and of course, they have nothing to lose, right? I mean, this is me getting myself there through Georgetown. I have the ability to stay. All she had to do was offer some collaborative space, okay? Offer me a cubicle. And so that's lesson 1. So I'm there for half the summer, 6 weeks, something like that, 6, 8 weeks. And along with that, while I was there, there's one day where I'm sitting in the cubicle, and before, you know how you just can be so immersed in your work that you don't notice, but this day, my eyes are more open, and there's a sheet of the statistics faculty just hanging up in the cube, And what you have to appreciate here is that the University of Oxford was a powerhouse, it still is, a powerhouse in statistics. Okay, but I'm seeing names, you know, of all of textbooks that I've had as a grad student, or, you know, they've developed the statistical softwares and work, and, you know, just prominent names. And so I sit there again at my computer. I reach out to some of these names to see if I can connect with them. And in my email, I even say, even if I can't, you know, let me just at least recognize you, basically give you your flowers, as the children say now, give you your flowers to recognize the great work that you've done and the impact that you've had in the discipline. But guess what? One of those faculty on the list is David Cox. Do you remember me talking about David Cox? So with David Cox, he gets a different email. He got an email, so lesson 7, I should also say, utilize the network of your colleagues, your allies, your advocates, all of the above, okay? And what do I mean by that? It's worth saying that with Cox, I'd actually connected with him on at least one other occasion at this point. And there's also worth noting that he and my advisor did know each other too, okay? And so whenever I would reach out to him, meaning Cox, I would always reference my former advisor, okay? Because, you know, name dropping, I'm not above name dropping, right? Whatever works. And what did I do in the email? I sent him that picture, because yes, I still had it. You thought I lost that thing? I still had this picture. And I sent it in the email, and I was like, oh, I'm here in England. I'm here at Oxford, and it would be so wonderful to connect with you. Well, guess what? He wrote back, oh, wonderful to hear from you. Why don't we have lunch? So we had lunch. I had lunch with Sir David Cox, okay? And yes, I do remember the day, and you'll understand why in a second. July 23rd, 2015, we gather for lunch, and we're catching up on life and work and all of the above, noser and otherwise. And then we get into the conversation about my work. Well, what is it that you're doing now? And I tell him about some of the work, and oh, that sounds really interesting. Can you send me some of your papers? Sure. Okay. And so we have a lovely lunch. And at the end, I should also note, I was like, this would not be, I could not let this time go by without doing what? Getting another picture. So we got another picture, obviously this time a selfie, and we part ways. But like I said, now remember, what did he do? He asked me for copies of my work, okay? And so that takes me to lesson 8. What is lesson 8? Do your homework. Just because I'm no longer a student doesn't mean that I don't have homework. What was the homework now? To follow through on that man's request, okay? So I get back to where I'm staying. I email him a thank you note, because I should say he even paid for the lunch. And, you know, thank you so much. It was such a wonderful time. I send him the new selfie along with a couple of my papers. And why is this one so important? What happened the next day? So I go about my business. The next morning I get up, I go into my cube. I have 2 emails in my inbox. Now, I don't know if you can read this, it's a little small, but this first email says, in part at least, I won't read every word, Dear Kim, it was great to see you. Yes, we must not wait so long. Thank you for the selfie. Thank you as well for the papers, which I hope to read more closely. But you probably won't know, but I'm one of the editors of IMS, which is the Institute for Mathematical Statistics, and Cambridge University Press for their monograph series. How about putting together an account of these models summarizing the wide-ranging aspects of this Poisson, right? I shall ask the Cambridge editor to send you details on how to go ahead. Do think about it, please. Signed, David. Like I'm going to call this man David. And if that's not enough for you, like I said, there were 2 emails in my inbox. Notice this one is time-stamped July 24th at 5:22. 5 minutes later at 5:27, he has emailed the contact for Cambridge University Press, making her aware of me, telling her to follow up with me to write this book. So that is how the opportunity to write a book came to me, like it did. So 2 minutes later, some of you may recognize this reference, the SpongeBob. 2 minutes later. Yes, this is how I looked. This is how I looked. And it's worth saying, remember, I think it's now like 6 something in the morning because I am an early bird. So at 6 something in the morning, I'm freaking out, literally screaming in this cubicle because I cannot believe what has just dropped in my lap. And I'm like, I have to call somebody. Now, I can't do East Coast because that's 6 hours back, so it's midnight. So I go to West Coast and contact a colleague friend in California, and I'm like, you won't believe what just happened to me. And even she's freaking out. So this is how I look 2 minutes later. 2 months later, same look. Years later, same look. Why am I still looking like this for 2 years? Because like I said, this just fell into my lap. I had no plans of writing a book. And the idea of doing so, I'll admit, offered a sense of overwhelm and intimidation. What does that look like to write a book? I've never done this. This is outside of my wheelhouse. But what also occurred to me, I should offer for context, like I said, it's now 2 years later, okay? What I have not told you is that when Cox and I had that lunch, he was already 90-something and walking on his own. I have to say, that man was unreal, okay? Just all he had was a cane, walking around and still active, still had students, master's level. He wasn't taking Ph.D., but at that point, but still very active and engaged. But like I said, now it's 2 years later. And to have that man's backing, I knew meant a lot in the field. So if I need to put up or shut up, if I'm going to do this, I need to do it, with him as my advocate. And so now the question becomes how to move forward. So lesson number 9, don't make things harder than they need to be. I was in my own way in terms of trying to do this, right? I just had to let that go and lean back into that network that I have. So you remember what I said about networking, right? Well, networks can be both within and outside of the discipline. 2 such people that were influential for me at this time are Monica Jackson and Chris Marsh. Monica Jackson, some of you know, she is also a mathematician or statistician, depending on the circles. She too got her degree from the University of Maryland. So, Misha, you might remember her. And she had written with some colleagues an introductory statistics book. So she was just a little ahead of me in this process. But meanwhile, Chris Marsh, she is actually a sociologist and demographer from the University of Maryland. And we just happened to meet for outside reasons. We wound up on a different advisory board for an organization together. Well, with Chris, it turned out the timing was absolutely perfect, where we now call ourselves academic or author sisters, because she too, at that time, just got a book accepted for publication through who? Cambridge University Press, but in her area, okay? And so I'm with Chris saying, well, can I see your proposal? What does this look like? She let me see her proposal. She let me see the format and how she wrote it and how you want to motivate. And so that helped. And then, I send the proposal to Diana, and Diana says, oh, well, that's great, but I need a couple of chapters to go along with this so we can see how the book can flow and, if there could be interest. So now I'm working on some chapters. But again, I needed that guidance. I had no idea how to do this. And so that was such a huge help. And so finally, for lesson 10, trust the process and see it through. For the next 5 years, Chris and I were cranking out our respective work on our books. And I show this almost quite literally. I mean, we have to settle for the animations. Although when I say that we were on Zoom together, like all day, every day sometimes, because I don't know that you've noticed, the time lapse takes us into COVID. So during COVID, we are literally on Zoom, keeping each other company. It's our means for social interaction and productivity, keeping each other accountable. And so we each even finished our books about the same time. And if memory serves, her book came out in February of 23. Mine came out in March of 23. And so we are literally, like I said, Cambridge sisters. At least that's what we call ourselves. Okay. In terms of the contents of my book, it's really just capturing and encapsulating many of the different ways in which the distribution has been utilized. Much of that work, I have involvement in a lot of the work, but not everything, because there are others out there that are doing the work. So of course, that notion of publish or perish is a whole nother side discussion that we can have when it happens in real time. It's quite a fit. But nonetheless, so yes, this is the makeup of the book. Now, further, let me remind you again, what was lesson number 7? To utilize that network of allies and advocates. Well, remember what I said before, they don't all have to be from the discipline. And so they are your support system. Now that the book is out at this point, all of my friends are so excited. And it's worth saying, I have many friends in the discipline, but of course I have even more outside of the discipline, right? But they are all so excited at the idea of me doing this book, they want to, offer some means of support. So this is how you get stuff like this. I don't know, can we increase the volume somehow? Maybe it doesn't matter so much. You have intense music in the background, just imagine that. So to explain what you're seeing, it's basically a movie preview, but for my book. And it's worth saying this was not done by me because, of course, I don't have this skill set. Chris had the idea because she did something similar for her book. And then an artistic friend of mine took the leap of creating this preview, if you will. Okay, so for me, I just found it as a good laugh because it's amazing that anyone would go to this effort to promote a math book. I had to remind people, this is a math book, right? And why do I bring that up? You'll see in a second. See, it goes on to March, and it even shouts out my family, family and friends. And so it was quite an experience when the book finally came out. This is just one of the traditional ads that IMS and Cambridge used to promote the book. But like I said, when friends finally found out that the book was out, they put themselves out there. So much so, I was even #1 on Amazon for a while. What? What? Again, this is a math book, right? But I can claim it. For a time, I was #1. And friends just put themselves out either to me privately or on social media, buying their copy of the book. And like I said, I have the best support system out here. friends, and here's my family when they got to see the book. And so again, I figure I'll at least give you a live shot of me looking the way of the animation. But of course, I was very happy to finally get my hard copy. And if this wasn't enough, what else were friends doing as a support? Oh, you should have a book signing, a book release party. You know this is a math book, right? I kid you not, I actually had signage that read, you know this is a math book. One friend even asked me if I would read from it. I had to remind her that this is a math book. It's not going to come across in quite the same way. The probability that X equals X is, yeah, it just doesn't have the same oomph to it, right? And I should say, for many of them, they even said to themselves quite humbly, I know I can't get past, the dedication, or the beginning text or table of contents. They're like, I don't understand anything in this book. But the fact that they still bought it just shows they were just so proud of me and what I had accomplished. And what you're seeing here is just some of the pictures that took place from that celebration. And I should say, I mean, they had to push me to do this because in my mind, I wrote the book, but then I was ready to move on to the next thing. And they're like, no, you need to celebrate this. This is huge. And so in particular, what you're seeing are, Dr. Johnson, and here's many of the Maryland cohort that came out to support me. But I had more friends and family also at this event. And so, yeah, it was, like I said, it's just a full circle moment to celebrate this. So to close, what I hope you've learned in terms of tips, shall I say the 10 tips, don't be afraid to put yourself out there. Don't make the same mistake twice. Don't let a detour derail you. Get to work, build that network, stay on your grind, utilize that network, do your homework, don't make things harder than they need to be, and finally, trust the process. Thank you so much. I'm realizing I forgot these slides. So this was to tie back to that example that I gave. For that and many other reasons, I've come to describe myself as an outlier personified. So obviously a play on words yet again. But I later changed this because I realized that there's more to this context of being an African-American woman in this discipline. And so I now call myself an outlier, forever striving to be an influential point. Now I'll say thank you.
Well, when this talk started, I didn't think it would end up by saying sister, because I published a book with Cambridge University Press, and my editor was Diana Gully.
Oh, isn't she wonderful?
At some point I'll tell you the story, maybe over dinner.
Yes.
I connected. So we are publication siblings.
There you go. Yes.
So I'm sure she'll be excited.
Oh, she will. We'll have to take a picture together.
All right. Well, I should not go too much on my own publication. Questions from the audience for Professor Sellers?
Yeah. So the model, the COM model that you were developing, how reliable is a model like that in terms of predicting future outcomes?
Well, I mean, you're talking to a statistician, so I'll argue as reliable as any other model, right? Because in truth, right? Because any model is built based on the existing range. When you get into forecasting, I mean, there's a little more effort that is involved there. So, yeah, perhaps that's the easiest way to answer the question. But certainly we could build something and think about what it means to forecast. We've not looked at things in that space as of yet, which is the blessing and curse of this model. I can literally use this for anything. And so it's just a question of having the time and the bandwidth. So of course now, especially being a department head, to 50-ish faculty and staff and 500 students, it's a little difficult for me to protect some time and still get some work done, although I am still doing some research too. Yeah, but thank you for the question. Bill.
Mathematics, statistics, mathematical statistics. How do you define them and where do you draw the line?
Ooh. So, sure. For me personally, that is probably somewhat of a difficult question just because of my background and just my general nature. I'm very inclusive just by definition, right? So notice that I somewhat span the entire arc between mathematics and statistics. I will grant you that I lean more on the stat side than the math side these days, and I recognize that purely just from a place of where and how I engage with others. I am far more at the joint stat meetings versus the joint math meetings, for example. Obviously, I do go to joint math every now and then, but you can probably find me at joint stat every year, at least every year possible. And certainly when I walk in that space, there's a different recognition too. I can't walk from one end to the other without getting stopped at joint stat. Math it's easier for me because again, I'm probably viewed as more being in the periphery in the math space, which is fine because I mean, in math, there's so many subdisciplines, right? Of which statistics is one or probability is one. The beauty of it for me is that I am not so strict about the categorization. So it gets back to the point that we were making before in terms of how the data are even collected. As statisticians, we bleed into other areas anyway. And so for me, that bleed is into math. That's how I look at it. Yes?
I'm curious to know if there's any oral histories or other recordings of CARM. That sounds like the Worcester Conference of African Americans in Research Mathematics.
Mm-hmm.
That seems like a big deal. I mean, you're pointing out all the people who were there.
Oh,
Is there
yeah.
anything more about that?
I'm happy to say yes. And I say that because I Googled it before coming. So, yeah, so there is still information online. If you just say, so I can tell you explicitly, I Googled who was at the first CARMs, because here it is almost 30 years later, and I was struggling to remember some of the names. And I was like, oh, thank goodness, this exists. So, but yeah, there were some heavy hitters there at the time. And like I said, David Blackwell was there. I mean, how well people would necessarily know names, I'm not so sure. But if you read about some of their histories and what they did, like, it's very humbling. Yeah. Yeah, I guess if you want a couple names, I'd say look up J. Ernest Wilkins. He's one. And let's see, Lee Lorch. He's an interesting read. It's funny, I've seen some handouts like, oh yeah, yeah. These were some doing some interesting work, and all not only in the disciplines themselves, in their areas of math, but also just how they work to help and support African Americans in the field. So let's see, I'm trying to remember who else. I mean, but yeah, you could, like I said, the information is available online. Yeah, for me, Dr. Johnson is a huge one, and arguably for anyone, but of course personally for me, just because he was a mentor to me even as an undergraduate. So I didn't explain. It was noted that I did my undergraduate degree at Maryland. Well, at that time, I was the only African American undergraduate math major, and Dr. Johnson was the only African American professor in mathematics at Maryland. It's also worth noting that in my junior year, that's when he became chair of the math department. And as a result, he was the only African-American chair of a math department at any predominantly white institution in the country. And so what that did for the graduate program in math at Maryland was significant, doesn't even give proper context. We wound up, and I was witnessing that as an undergraduate. I started seeing more African Americans in the math building, even as an undergraduate. And so for me, staying at Maryland took a different meaning, because admittedly for me, part of the take was, I've already proven myself as an undergraduate, so I didn't have to go through the process of proving myself to the faculty at Maryland, because they already knew me now. So for me, that was a different lift and draw for staying. But I wound up being one of, it was either 6 or 8. I'll admit, everything's running together these days. So for as much as I work in count data, I'm losing it from a personal space. But yeah, there were like 6 in my year, and I think 5 the year before. The department got as high as, I think, 25 in the department. And you just didn't hear those numbers. But Maryland was second to Howard at that time in terms of the most students in the math programs. And so, I mean, we were literally studied, like researched by some disciplines, trying to understand what was that secret sauce in terms of having such a large cohort of students. And so, yeah, it was quite an experience. And then even though I didn't finish there, I did finish with a master's, but still kept in touch with those friends that I had made at Maryland, and obviously still do. I mean, Monica was one of them. Please.
Okay, so since you're interested in small chunks of data, I was struck by the 2 icons. They all seem to do rather well on the longevity scale. So do you have any observations of this? Statistics, and I've done statistics, so I want to go on life. This builds at my age.
Well, I'll offer this much. You also saw a picture of my father in there. My father is not a statistician, but he too has longevity to his credit, and is still with us at 96. So I tell him all the time, I hope he passed all of that to me.
Thank you, Professor Sellers, again.
Thank you. Thank you.